Hello and good morning, good afternoon and good evening, depending on where you live on Earth, and thanks a lot for being on board for this Device Tree 101 webinar. My name is Thomas, and I'm very happy to have you for the next hour and a half or 2 hours talking about Device Tree. I'd like to first introduce myself. I am Thomas Petazzoni, the CTO at Bootlin, which I joined in 2008. At Bootlin, in addition to being the CTO, I am also one of the members of the engineering team, acting as an embedded Linux and Linux kernel engineer. In this position, I have been the author of the Device Tree for Dummies talk in 2013-2014. And in fact, this webinar today is an update on this talk in an extended version. It's like twice longer with more up-to-date information and more detailed information. I am also one of the co-maintainers of Buildroot, an embedded Linux build system, and I have contributed over 900 patches to the official Linux kernel, and it is based on this knowledge of Linux kernel contribution that I've learned a number of things about the Device Tree, which I will be sharing with you today. I am also a member of the program committee for the Embedded Linux conference, both US and Europe. Finally, I am based in Toulouse in the southwest of France. Today, we will be talking about different topics around the Device Tree. I'll start by introducing Bootlin, then the STM32MP1 family of processors, which we will be using as illustrations for the different Device Tree examples. We'll talk about why we have the Device Tree, what is the base syntax of the Device Tree, the concept of Device Tree inheritance, Device Tree specs and bindings, the interaction between device trees and Linux kernel drivers, and we'll have a significant discussion around the device tree properties and a number of examples as well. And finally, we'll close with a Q&A session, and you'll be able to ask questions on the chat, and I'll answer as many questions as I can. So first, let me introduce briefly Bootlin. We have been in business since 2004, and we are a consulting company specialized in embedded Linux engineering. Our team is based in France, but we have customers worldwide. We make less of 20% of our revenue in France. Everything else is in the European Union or even elsewhere, US, Canada, and other parts of the world as well. Our expertise is highly focused and recognized, as our focus is exclusively on embedded Linux low-level development. So we do Linux kernel development, bootloader development, and embedded Linux system integration, mainly with build systems such as Yocto or Buildroot. Our activities are training services, which are approximately 20% of our revenue, and everything else are engineering projects where we help our customers bring embedded Linux to their platforms, which is the rest of our revenue, approximately 80%. So first, let's talk briefly about our training offering. As of today, we have 6 different training courses that are available. A first course that introduces to embedded Linux system development to understand the different components in an embedded Linux system and how they work together. A second course about Linux kernel development, how to write device drivers in the kernel. A third course about Yocto, how to use Yocto to build an embedded Linux system and integrate the different components together. A fourth course about Buildroot, which is following the same idea as the Yocto project course, but applied to an alternative tool, Buildroot, for building an embedded Linux system. We have a course dedicated to the Linux graphics stack to understand from the hardware all the way up to user space the different components that make up the graphics stack of a Linux system. And finally, we have a new course that we announced last week on embedded Linux boot time optimization to learn tips and tricks to optimize and reduce the boot time of embedded Linux systems. All of those courses are available on site when the travel conditions make that possible, or currently also online, so that we can continue deliver those courses to the companies and engineers who need that. So why would you choose the training courses from Bootlin? We have a few things that make them quite unique. The first and probably most important thing that makes them quite unique is the fact that all our training materials are freely available. We deliver them and distribute them under an open source license, the Creative Commons by SA license, which allows everybody to read and use and reuse those training materials freely. It allows everybody to verify in detail the contents of the course before maybe purchasing our course, but it also allows everybody without purchasing our course to access all this knowledge. So it shows our commitment at Bootlin to knowledge sharing, and again, this is quite unique in the training industry. Second, Our courses are delivered by experienced trainers. Contrary to a number of training companies where the trainers are only trainers, at Bootlin the trainers are all also engineers. They spend the vast majority of their time at our offices working for our customers on real engineering projects. And only from time to time they deliver training courses to our customers, which ensures that they have an up-to-date and in-field experience. Finally, our courses are recognized worldwide. We have delivered hundreds of sessions to many customers all around the world, to thousands of engineers for the past 15 years. In addition to those training services, we also have engineering services, where our main activities are around the development and delivery of complete board support packages for our customers. Our customers come up with some kind of custom hardware platform. We port a bootloader, we port the Linux kernel, we write kernel drivers when necessary. We do the system integration with Yocto and Buildroot. We might work on boot time optimization, integration of secure boot mechanisms, and others. In addition to doing this Linux board support package development and delivery, we are also able to work on upstreaming the appropriate changes to the relevant open source communities, the Linux kernel, U-boot, Yocto, Buildroot, and others. And this allows to offer our customers a long-term maintenance of their BSPs. In addition to that, we offer consulting and technical support on this really low-level part of the software stack, bootloader, kernel, and build systems. Our customers are mainly silicon vendors who contract us to develop hardware support in U-boot or Linux for their hardware products, and usually also as contractors to upstream that support so that it is available directly in the official versions of Linux and U-boot for everyone to use. And the second category of our customers are embedded system makers who produce embedded systems that go in the wild in the healthcare industry, transportation industry, in the home automation industry, and many others. And for those customers, we deliver complete BSPs, we develop custom drivers, debug, optimize, and provide our consulting services. Bootlin is not only a company delivering services to its customers, it is also a very strong open source contributor. We are actually the 20th contributing company worldwide to the Linux kernel. And you can see on the right of that slide the list of companies who contribute to Linux by number of commits since the Linux kernel started using Git to manage the changes in the source code. And with over 7,600 patches, we are indeed the 20th contributing company in the world. Not only we contribute patches, but we also participate in having some of our engineers be maintainers of several subsystems of the kernel. We are maintainers of the I3C subsystem, the RTC subsystem, the MTD subsystem, and several platform support code as well. We are a key contributor to Buildroot. I am myself the co-maintainer of this project, and collectively at Bootlin we have contributed over 5,000 patches to this project over the past 10-12 years. We contribute also to Yocto, to Barebox, to the Linux test project, to U-boot, and a few other open source projects as well. As mentioned earlier, our training materials are all freely available, and we also give numerous talks or webinars like this one freely at different conferences to share technical knowledge, technical content. So with this introduction of Bootlin done, I would like now to move to the introduction of the STM32MP1 platform. The reason why we're taking this as an example is because this webinar is organized today in partnership with ST. So thanks a lot ST for supporting this event, and that's the reason why we will use this specific platform to illustrate the different concepts of the device tree that we will cover throughout this discussion. ST originally has a very strong background in MCU, microcontrollers. They have a wide portfolio of products, they are very popular, but in 2019 they decided to extend their offering of microcontrollers with microprocessors that they call MPUs. And the first family that they started in 2019 is called the STM32MP1 family of processors. It is a family of system on chip based on ARM, of course, that provides a wide range of functionality. The one that you see for now on the slide, the STM32MP157F, is kind of the higher end variant of that family. You can see on the block diagram, it is a dual A7 core at 800 MHz. It also has a Cortex M4 at 200 MHz so that you can run real-time applications side by side with the Linux system running on the dual A7. It has a GPU It has a wide range of IP blocks for connectivity, for display over RGB interface or DSI, a camera interface, gigabit Ethernet, HDMI, CAN, SPI, I2C, MMC, and audio interfaces, ADCs, DACs, PWM, and security features. So plenty of functionality available in this SoC. This system on chip, as I mentioned, is part of a wider family, the STM32MP1 series. And having an understanding of this family is quite important to understand later in our discussion the organization of device tree files. So we have 3 different variants of the SoC, the 151, the 153, and the 157. So the 151 is the lowest end in the series. It has only a single A7. It has no GPU, no CAN interface, and no DSI display interface. Then the 153 on top of that brings 2 cores, 2 A7, and brings 2 CAN interfaces. On top of that, the 157 brings the GPU and the DSI display interface. Then within each variant, you have the A and the C, which the A doesn't have any security mechanism, so it doesn't have hardware crypto support or secure boot support, while the C has the security mechanisms. So that's true for the 51, 53, and 57. And then, as you can see again on the table, there are for the variants D and F, which are the ones clocked at 800 MHz. So there's a variant at 650 MHz for the clock frequency of the Cortex-A7, and an 800 MHz variant for the clock frequency of the Cortex-A7. So that really gives a range of choices depending on the applications and the performance level and the features that you need for your project. Based on these SoC, ST has put together a number of different evaluation kits, and especially 2 discovery kits, the Discovery Kit 1 and Discovery Kit 2, which are relatively inexpensive evaluation boards for these SoCs. So let's start with the DK1 on the left side of the slide. This DK1 is using the 157A SoC, which is almost the highest end one. It's just that it doesn't have the security aspect. It has half a gigabyte of DDR, it has a micro SD slot, gigabit Ethernet, USB-C, USB-A, LEDs, buttons, HDMI, audio, a DSI connector for a display. And on the back side, it has Arduino, Raspberry Pi Shield compatible GPIO connector. So you can plug extra expansion boards that are widely available for other families of evaluation boards like Arduinos and Raspberry Pis. On the right side, you have the Discovery Kit 2, which is based on the same SoC, just the secure variant of it. So it has the crypto engines and secure boot capabilities. Overall, it has the same capabilities as the DK1, but it adds a Wi-Fi Bluetooth chip, and it adds a display and touchscreen, as you can see on the picture. So if we put that on a block diagram, of course, the partial block diagram, it definitely doesn't show all of the features, but I think it's important to keep in mind this view of block diagrams, that this is important to understand then the concept of device tree. We have at the center of the picture the system on chip itself, the STM32MP1 57C, which includes a number of hardware blocks, GPIO controllers, Ethernet mags, MMC controllers, I2C controllers, and many other hardware blocks, all around the CPU cores, of course. Then this SoC is put on a board which has a number of components, such as DDR memory, a display panel, a power management IC, a Wi-Fi Bluetooth chip, micro SD slot, an Ethernet PHY, a touchscreen controller, and others, which are represented in green on that picture. So that is important to keep this view in mind for the rest of our discussion. Some hardware buses provide discoverability mechanisms. If you have already used or worked with USB or PCI, perhaps you have realized that when you plug a USB webcam into your system, you don't need to tell your system anything about that webcam. It is able to automatically detect that a new device has been plugged into the system, and then enumerate that device and discover what this device is, and therefore identify a driver that would make sense to manage that device. This is possible because USB and PCI both include discoverability and enumerability mechanisms. So the CPU that has a USB controller or a PCI controller can use the capabilities of the PCI and USB buses to query which devices are connected on the bus and what their identifiers are. So typically in the USB and PCI world, each device that is produced has a unique vendor ID and product ID, which allows to uniquely identify, okay, this is this specific model of that webcam, and therefore find a corresponding driver for it. So that's very nice. And on Intel x86 platforms, a significant amount of the peripherals on a system are indeed connected over PCI and USB. But there are also many hardware buses that do not provide such dynamic discoverability mechanisms. For example, I2C, SPI, one-wire, or memory-mapped buses and devices typically don't offer such discoverability mechanism. So one needs to know ahead of time what are connected to those buses. If you have an I2C bus with 2-3 components connected to it, you cannot ask on the bus who is there and who you are. You have to know that by design and how those components are connected to the rest of the system. And it turns out embedded systems make extensive use of such buses that don't support dynamic enumeration. So the description of non-discoverable hardware is what will allow the operating system or bootloader to know things like, okay, my system is composed of a system on chip, which itself contains 2 Cortex-A7 CPU cores. It also contains maybe 2 UART controllers, which are memory mapped, and the first one as it's registered at that specific address, and it is using this interrupt line of that interrupt controller. And it has another UART controller at this other address and using this other interrupt line of that interrupt controller. But it also has 3 I2C controllers and maybe, I don't know, SPI controllers, MMC controllers, display controllers, and so on. And in addition to knowing what is inside the system on chip, we also need to tell the operating system or bootloader what is on our board around the system on chip. Maybe I have an audio codec that is on some I2C bus, so it is connected on a given bus at a given I2C slave address. It is connected to a given audio interface of the system on chip. Maybe it has a reset signal that is connected to some GPIO of our system on chip. And all this connection and integration of our audio codec with the rest of the system needs to be described somewhere so that the operating system or bootloader knows the topology of our hardware. All those details simply cannot be guessed or figured out at runtime, at boot time, by the operating system or bootloader. So how do we provide this information about non-discoverable hardware to our operating system or bootloader? The first possibility is to simply hard-code it and code it directly into the operating system or bootloader code using compiled data structures, typically in C. And that is how it was done typically in the Linux kernel for ARM platforms. We were writing C data structure, each describing one device after the other. So when you had, for example, 4 UART controllers, you would write 4 C data structures that would each describe one of these UART controllers with their characteristics such as addresses of registers, interrupt line, DMA channels, and any other thing that describes them and allows the Linux kernel to use those UART controllers. With the expansion of the number of ARM SoCs, the expansion of the number of ARM boards, the size of those files describing all those devices became a bit overwhelming and difficult to maintain. And so the ARM community in the Linux kernel tried to find different approaches to solve this hardware description problem. So another solution that exists is using ACPI tables. This is widely used on x86 systems where your BIOS or UEFI firmware passes to the operating system a set of tables, ACPI tables, that give the operating system knowledge about the hardware that cannot be discovered. This is also now being used on some ARM64 systems that are oriented towards the server market. It is somewhat less used for the more embedded market, that being said. An issue with ACPI is that on x86, as I mentioned earlier, the vast majority of the hardware being on PCI or USB buses, it can be discovered dynamically. And only very few aspects of the system had to be described in these ACPI tables. Therefore, the capability of ACPI tables to describe complex pieces of hardware was kind of limited, and it has been extended and improved since then. But when we started using the device tree in the kernel, it was not that advanced. So obviously the last possibility, and the one we'll be discussing at length today, is to use the device tree. It's something that originates from open firmware, which was defined by Sun Microsystems, used on the Spark architecture, and then on PowerPC. So it is not a technology that comes from the Linux community. It is really something that has been used before. And this name, open firmware, is sometimes reduced to just OF, and that's why there are many Linux or U-boot functions that are related to device tree that have this OF prefix. Which is sometimes confusing when you don't know that relates to open firmware. This device tree mechanism for describing non-discoverable hardware is now used on the vast majority of embedded-oriented CPU architecture that run Linux, from ARM32 to ARM64, but also RISC-V, PowerPC, Xtensa, MIPS, ARC, and pretty much all the other CPU architecture that you can imagine. And indeed, it is in fact now mandatory to use the device tree if you want to contribute support for a new CPU architecture in Linux. So writing, modifying, tweaking a device tree has now become something that is necessary whenever you want to port Linux to a new board or simply connect additional peripherals to an existing board. And that is precisely what we're going to cover in this talk. So the device tree at the beginning is a piece of source code. It is a tree data structure that describes the topology of the hardware, written in a source file called a device tree source, DTS, and the extension used is simply .dts. This source file that is written by a developer who knows the hardware, who knows the topology of the hardware, is not directly used by the operating system. Instead, it gets compiled into a more efficient representation. So the compiler is called DTC for device tree compiler, and it produces that more efficient representation that we call device tree blob, DTB, which ends up being stored in files with .dtb extensions. There is an extra C preprocessor pass, in fact, that is done before DTC in most projects, so that we can use sharp defined macros and use such macros to make the device tree more readable than using hard-coded values all over the place. And then this DTB that we get, device tree blob, is meant to accurately describe the hardware platform in an operating system agnostic way. So that is another key design principle of the device tree. It is not tied to a particular operating system. The device tree blob describes the topology of your hardware, what your SoC is, what it contains, what are the different hardware blocks, how they interact with each other, and what is on your board around the system on chip. To give you an idea, a typical DTB describing a board is around a few dozen of kilobytes, so it's a fairly small representation, it's not huge. This DTB is also sometimes called FDT for flattened device tree, once it is loaded into memory. So you will find in different places, like in U-boot, there are some commands named FDT for flattened device tree to manipulate the device tree. There are APIs named FDT underscore something that also exist. So that's why I insist on that terminology as well. So let's take a quick example of a very basic device tree that doesn't even represent any hardware platform, right? The device tree compiler doesn't care about what is inside your DTS, it does only syntactic checking on it. It doesn't know the semantic of the device tree language. So my very simple DTS here starts with a mandatory statement, DTS-v1, giving the version of the device tree language we're using, and I think v1 is the only one that exists. And then our tree starts with a root node that starts with /, and this root node has a number of things inside, which are properties and subnodes. And we'll get into the details of the syntax of the device tree later on. But let's assume for now I have this device tree. I can then use DTC, the device tree compiler, to compile it. So I invoke DTC, specifying that my input is a DTS-I DTS, that my output is a DTB-O DTB, and I build my device tree this way. So you can see the size of my device tree. The source was 102 bytes. The DTB is a little bit larger, 169 bytes, but it's still a fairly compact representation. Then, once I have this DTB, I can in fact kind of decompile it again with DTC, specifying that my input is a DTB and my output is a DTS. So it's, I know, decompiling foo.dtb and getting back pretty much the same representation as I injected in DTC at the beginning. So kind of almost a two-way conversion process is possible. It's not exactly the same case, but for the most part, you can decompile a DTB like is shown here. So now that we have this DTB, how it gets used by bootloaders or operating systems. So bootloaders can use it, or firmwares can use it to, just like Linux, get an understanding of the topology of the hardware. Which serial ports do you have? Which MMC controllers do you have? Which one do you use to access an SD card or an eMMC? All this information needs to be known even by something as simple as a bootloader. Typically, bootloaders such as U-Boot or Barebox will directly link a DTB inside their code because they don't have access to a file system to load the device tree. So what they typically do is simply bundle up the device tree into their code. For Linux, it's a bit different. For Linux, the DTB is typically passed separately from the kernel image itself. So if you take the case of U-Boot booting Linux, which is probably a very common situation, what happens is that you will have to load a kernel image, which is the image containing the code and the data of the kernel. Separately, you will have to load a device tree blob that describes the particular hardware platform you want to boot on. So load both of these information in memory. So in the example here, we have kernel ADDR for the kernel code and data, and DTB ADDR. And we pass those two addresses to bootz, which is the command in U-Boot to boot a Linux kernel on ARM32 platforms. The dash in the middle is just to tell U-Boot that we are not using any init_ramfs for booting. We're just using a kernel and a device tree blob. And when you enter this command, U-Boot is going to jump to the entry point of the kernel. But before doing that, it is going to store in a specific register, which is R2 on ARM32, the address at which the DTB is located. Thanks to that, when the kernel starts, it receives the address of the DTB in RAM, and it can access the DTB and parse it to discover the topology of the hardware. The bootloader has the ability to adjust the DTB before passing it to the kernel, and we'll see a few examples later on, but basically this means that the DTB that the kernel sees may be slightly different than the DTB you have stored on your file system, as the bootloader can do on the fly a few changes to that DTB before handing it over to the kernel. Then the parsing of the DTB can be done using a library called libfdt, which is provided as part of the device tree compiler project, and you can include it into your bootloader or operating system kernel, or using ad hoc code as is done in Linux, because the DTB representation in memory is pretty simple and it's not very complicated to parse. So these device tree files, for sure, you could write your own, but there is plenty of existing hardware platforms that are supported in Linux and in other projects. So where do you find those existing device tree files? And as I mentioned, the device tree is supposed to be an operating system agnostic representation of the hardware. So ideally, there should be some kind of reference place where you can find the device tree representing various hardware platforms. Sadly, that doesn't exist. There is no such central and US neutral project or location that was created to collect all those device tree files. So this was discussed many times, but never done for various reasons. So in practice, it is actually the Linux kernel sources that kind of serve as the canonical location reference for device tree files. So in Linux, if you look in Arch, name of the architecture, boot, DTS, for various CPU architecture, you can find many device tree files describing a lot of different system on chips and boards. There are approximately 4,700 device tree source files in Linux as of Linux 5.10. And because those device trees are also used in other projects, they are typically duplicated, sometimes tweaked a little bit and synced from time to time into other projects. And that's what U-Boot, Barebox, TFA, which is the new name of ARM trusted firmware, and perhaps a few other projects are doing. So this is not optimal, obviously. Like in general, in open source, we don't really like duplication, but at the moment, this is pretty much what is happening with those device tree source files. So let's take specifically the example of one of these STM32MP1 platform, which I think nicely illustrates what is going on. So if we take the example of this Discovery Kit 1 board and look at how the device tree gets used in the different stages of boot, it's interesting. So we have several stages in the boot process. The first stage is TFA, so ARM trusted firmware. As a second stage, we have U-Boot. and then we boot a Linux kernel. And each of those stages need to have some amount of details on the hardware. Probably Linux is the one that needs the highest amount of details because it is the place where all the peripherals will have to be supported, from the basic UART all the way to your camera and display. Most likely TFA and U-boots require less support for devices, but still they need to understand the hardware they run on. So if we take the example of TFA to start. In TFA, the device trees are stored in FDTs, and we have one named STM32MP1 DT1 for the platform we are interested in. So when we want to build TFA for this board, we need to build it with plat equal STM32MP1, and then DTB file name and the name of the DTP we are interested in. So what this tells you is that if you look at the name of the platform, it only contains the name of the family of the system on chip. It doesn't even contain the specific system on chip we're using, and not even the name of the board we're using. So the code of TFA is relatively independent from the board and the exact system on chip we're using in this family. It is going to get the relevant details about the board and the specific system on chip we're using thanks to the DTB that will be bundled into the TFA binary. And indeed, the resulting file tfa STM32MP157A DK1.STM32 is going to contain the code of TFA, but also will bundle that DTB. In U-boot, things are pretty similar. We have a device tree. It's located in a slightly different place, but the idea is the same. We have a fairly generic configuration called STM32MP15 trusted devconfig, which is a generic configuration that works for all STM32MP15 platforms, regardless of the SoC you're using in that family, regardless of the board you're using. And when you build U-boot, you have to give a device tree environment variable that tells which specific device tree you would like to bundle inside the U-boot binary. So again, in the resulting uboot.stm32 binary, you'll get the U-boot code and a bundled DTB describing your specific board. In Linux, the DT are located in Arch ARM boot DTS, as I mentioned earlier, and the pre-existing configuration that exists for STM32MP1 is multi-v7 devconfig. As the name of this configuration suggests, it is a configuration that builds a relatively big kernel image because it supports all ARM v7 processors that the kernel can support, not only from ST, but also from many other silicon vendors that have support in the official Linux kernel. So you get a fairly sizable kernel image with plenty of drivers, and this kernel doesn't know a priori on which platform it is going to be booted on. But because you will load this kernel image, the image in memory, next to a device tree blob that describes precisely the platform you're booting on, the kernel will be able to identify which devices are available and instantiate the appropriate drivers. So booting on STM32MP1, that's a short boot log just to illustrate kind of in practice what that means. So here I have just U-boot starting up on that board. This U-boot by default comes with two environment variables that give two physical memory addresses which you can use to load the kernel image and the device tree blob. So kernel ADDR and FDT ADDR are at different positions in memory. I can load the image, the kernel image itself, and you can see it's like 4.2 megabytes. So this is really the code of the kernel and the data of the kernel. Then at a different location, I load the device tree blob, and you can see the device tree blob is just 53K, so it's quite small and quite compact representation. And then if I want to start up the kernel, I simply invoke bootz, passing the address of the kernel image, dash, because we don't use any initramfs, and the address of the device tree blob. And then when I boot, U-boot tells me, okay, I have found a kernel image at C20000. I have found a flattened device tree blob, so FDT, at C4000. It is going to boot with that device tree blob. And then it starts up the kernel. The kernel announces that, yeah, this is Linux version 5.8.13. And it's telling us which ARM core we're running on. But also very shortly after the build, it tells us OF, Open Firmware, FDT, flattened device tree, that's why I insist on the terminology and acronyms, and then machine model, and it gives us a long string describing the platform. And this long string comes from the device tree. There is one place, one particular property of the device tree that you can use to tell the human readable name of the platform we are running on. Once you have booted Linux all the way to a prompt, sometimes it is quite nice to be able to see the device tree that Linux is seeing. Because you have your DTS, you have your DTB, but as I told you, the bootloader can make some changes, or maybe you're not really sure you updated your DTB correctly. So you want to really check what device tree the kernel is seeing. And you can do that by going into the sysfs file system. If you go in /sys firmware device tree base, there is a directory file representation of the device tree currently seen by the kernel. And in this representation, every node of the device tree is going to be a directory you can cd into, and every property of the device tree is going to be a file that you can cat to see the actual value. So you can do that by just using cd and cat to navigate in the nodes and properties. But if you have DTC, the device tree compiler, available on your target hardware, you can also ask it to decompile or unpack that device tree representation by doing DTC-I fs, where fs stands, I have a file system representation of the device tree, and I would like to have the corresponding DTS. So it can give you that DTS representation of all these files and directories. That's quite handy for debugging. So now that this overall introduction of the device tree is in place, let's dive more precisely into the syntax of the device tree. In device tree, you have tree, and indeed, the device tree is a tree of nodes that are included into each other. On the right side, you can see that we have a root node that starts with /, and it encloses two child nodes, node at 0 and node at 1. Node at 0 happens to have itself two child nodes, child node at 0 and child node at 1. So we can enclose as many child nodes as we need depending on the hardware we need to represent. Inside those nodes, we have properties which are basically key equal value pairs. Each property has a name and it has a value. These values can be strings, can be list of strings, can be integers, can be list of integers, and they can also be Boolean properties, such as the first child property that you see. It doesn't have any value. It's because it is the existence of the property that makes it a true property, while if it's not present in the device tree, it will be considered as false. And more or less, you can see a mapping between a device tree node representing a device or an IP block into your system, and a property inside that node providing the characteristics of that device. And this is quite important to keep in mind, because if you remember the block diagram that I gave of the SoC and the peripherals around it, pretty much every square of that diagram is going to be a node in that device tree, because these are the hardware blocks that you have on your system on chip and on your board around the system on chip. There is the notion of cells in the property values, which I'm going to cover in more details later. The notion I want to cover now in more detail is the concept of p-handle. If you look at the second node, node at 1, it has a name, node at 1, but it also has a label in front of it before the colon, node 1. And this label is important because it can then be used by other properties to refer to that node. And this is done in the a reference to something property, which has as value ampersand node 1. This is what we call a p-handle. You can think of it as a pointer. It is a reference to something else in the device tree. And this will be very important to describe the relationship between hardware blocks in our system. For example, I am using a channel from a given DMA controller, and I am, I don't know, some kind of SPI controller, for example. Then I will need in my device tree to say, okay, I am an SPI controller, but I am using some resources from this other IP block in the system on chip. So we are going to use p-handles, these kind of pointers to other nodes in the device tree to represent these connections between hardware devices. Again, DTC only does syntax checking, no semantic validation. So DTC has no idea what properties are correct and what properties make sense or what nodes make sense. It can only validate that the syntax overall is correct, but if you make a typo in the name of a property or in the name of a value, it will simply not notice at all. So now that we have this basic syntax in place, let's have an overall look at the contents of a device tree. So on the right hand side, I have taken a very simplified view of a system on chip such as the STM32MP1, giving away many of the IP blocks and just focusing on a few of these. And then on the left side, we are going to see, I would say, aspect by aspect, how this particular hardware platform gets represented in a device tree. So on the left side, you have the root node, and then I have folded all the child nodes to make it possible to have this overall view of what we have in the device tree. So we've got these address cells and size cells properties, which can leave on the side for now because I have a separate discussion later on in this webinar. I have the model and compatible properties at the top level. The model property is the human readable string that we just saw in the boot log of the kernel. Remember, it shows OF, FDT, and then machine, model, and then a string. It comes right from there. Then we have the compatible string, which are identifiers for the platform as a whole. So here we have a unique identifier that says I am booting on the DK2 board from ST, and also this board contains an STM32MP1 SoC. And then the next nodes, some of them are specified by the device tree specification itself, and we're going to discover that later, and some of them are less described by the device tree spec itself, but by other documents. And it starts with defining the CPUs, then the memory, and then a node called chosen, and then we have a number of nodes describing hardware blocks. So I'm going to go step by step in all of those top level nodes. The first top level node is CPUs, and I guess it will be pretty obvious what it contains. It contains a description of the CPU cores we have. So here we have simply two A7 cores, and it describes, okay, each CPU at 0, CPU at 1. Both are ARM Cortex-A7. They operate at 650 MHz. They are CPUs, and we have a reg property that kind of gives an identifier. There's the CPU number 0, and there's the CPU number 1. The next node is the memory node, which is an example of a node that gets updated by the bootloader. So this node simply tells the Linux kernel what is the base address of your RAM and what is the size of your RAM, so that the kernel knows how much physical memory you have and where it is located, so that it can set up the page tables and the memory management units and do all its physical memory management, basically. And this entry is going to be updated by U-boot depending on the memory that U-boot has really detected. The next node, chosen, is a bit special because it kind of violates the rule that the device tree contains hardware representation. Indeed, chosen is there to allow the firmware or your bootloader to communicate information to your operating system. I'm going to start with the second property, stdout_path, which tells the kernel what kind of standard output it can use to display its messages, like the kernel messages you see at boot time. Very often in embedded, we like to have this on serial ports, so that says, okay, please use that particular serial device at that particular speed to show your messages. The other property, bootargs, is used by the bootloader to pass to the kernel the Linux kernel command line. So the kernel command line is this line of instructions where you specify root equal dev mmc blk0 p3 to indicate the location of your root file system, or many other kernel arguments. And so the way the bootloader uses to pass that information all the way down to the kernel is using this property. So your bootloader updates the DTB and specifically this /chosen/bootargs property so that it passes that kernel command line to Linux. Then we have our first actual, I would say not first because we already talked about the A7s, but another hardware block, the interrupt controller, which for some reason is not within the SoC node, but that doesn't really matter much. And so this node describes the interrupt controller. It says, I have an interrupt controller, it has some kind of compatible string, which we will discuss later in details. It has some reg properties with some addresses. I suppose there will be the addresses of the registers, and we'll talk about that later on as well. But that is one node describing this interrupt controller. Then we have a node called SoC, which itself has subnodes for each of the individual IP blocks that we have in the hardware. So the first one that we're going to describe is the I2C controller. So we have a node named I2C at 40012000, which has plenty of properties describing some details about this I2C controller. What is important at this point to understand is the fact that the audio codec that is connected to this I2C controller is represented as a subnode of that I2C controller. So this is what we call the topology of the hardware. We have a main system, it has some controllers. Those controllers allow us to connect to devices that are sitting on buses controlled by those controllers, and this is all represented in the hierarchy of device tree nodes. So an SPI device connected to an SPI controller will be represented as a child node of the SPI controller, and same here for the I2C. So our audio codec is represented by that node, which again has a number of properties describing various aspects of that specific device. And we'll get into the details of those properties as we move forward in that discussion. Moving on, the next hardware block that we have was the Ethernet MAC. So we have another node that I've unfolded here, which describes this Ethernet controller, which has different properties describing various aspects of this IP block. And connected to it, outside of the system on chip, we have the Ethernet PHY. And this is represented in a slightly more complex fashion here, in the sense that as a subnode, we first have an MDIO node. MDIO is the kind of protocol bus used for MAC to control and communicate an Ethernet PHY. So this is not the data paths where the actual Ethernet frames are going through, but it is really the control path that allows the Ethernet MAC to talk and control to the PHY, for example, detect if there is a link, what is the speed of the link, and things like that. So this is represented as a subnode, and again, as a subnode of that MDIO controller, we have the PHY itself, and its address, reg equals 0, indicates the address of the PHY on the MDIO bus. So as you can see, there is really, and I really like this approach of showing on one side the device tree, on the other side the block diagram, because there's really kind of a one-to-one mapping between a block diagram of your hardware and the device tree representation of it. So now that we have understood this concept of hierarchy of nodes representing the hardware and matching closely the actual topology of the hardware, how do we write those device tree files? We said there's going to be a DTS for each platform, and you compile it to a DTB, which you give to the kernel for it to understand the topology of the hardware. So far, so good. But it turns out that if you write a DTS for two boards that use the same system on chip, well, they are going to contain very much the same thing, right? Because they have the same processor. All the description of the hardware blocks inside the system on chip will be exactly the same for those two boards. So it doesn't make a lot of sense to duplicate that in multiple DTS files. So we want some kind of way of sharing that description. And obviously this exists. We have this concept of inclusion of device tree file. So in addition to writing DTS, we can write DTSI files for device tree source includes. And we typically use DTSI to store the description of an SoC or description of hardware that is common between several boards of the same family. And then we can include those DTSIs into our DTS to describe completely the hardware platform that we have in front of us. So the final DTS is the only one that can actually get built by DTC. If you feed in a DTSI by DTC, I think it doesn't even build it, or at least it doesn't make a lot of sense, as by convention, only a DTS stores board level information that you can build into a DTB and feed into your Linux kernel. This inclusion mechanism works by overlaying the tree of the including file over the tree of the included file. So in practice, this is just a sharp include directive. So once the C preprocessor has made it pass, you will have all the trees of the different DTSI that you include and the final DTS, like one after the other. But what happens is that if one tree overrides the property defined by a tree before it, it will really take precedence over the one that comes before. So that allows to override details that were provided by other DTSI. Let's make that more concrete on a real example. So on this slide, we have to the left, we have a DTSI file that describes a system on chip. Of course, it's just a very small part of it, but it describes an I2C controller of our system on chip with a number of properties. The one property that is interesting here is status disabled, because this hardware block is not enabled. Then in the middle, we have the DTS that includes the DTSI we just talked about. And in addition to including that file, it is also defining its own tree, which, as you can see, is very similar to the one before, right? The hierarchy is the same with a root node, then an SOC subnode, then an I2C at 40012000 node that is really the same as the one on the left side. But it's adding other properties. It's adding pin control names, pin control 0, pin control 1. Oh, and it's also adding a status equal OK. And this status equal OK is actually going to win over the status equal disabled that we had on the left. In addition to adding these properties, it's also adding another subnode, such as the audio codec that we have on our board. So the idea here is that in a DTSI, we describe what is inside the system on chip, regardless of which board it is put on. And on the DTS, we define how our board is using the different hardware blocks of the system on chip. And in practice, on that particular board, we are using the I2C bus number 1, and we connect it to an audio codec series CS42L51. So if you look at the compiled DTB, it is what you see on the top, the right of the picture, where we have basically the combination of bus trees. And what you have on the right is really what the Linux kernel will see. So this inheritance and overriding of values from a syntax point of view can be done in two slightly different ways. They end up doing exactly the same result, but just the syntax is slightly different. So the first way of overriding properties or nodes is by replicating the hierarchy. This is what was done in the previous example, and is shown here again. So you have a hierarchy / SOC serial at 5C0000, so that's the hierarchy of nodes in the DTSI. In a DTS specific to your board, if you want to override a property from that node, well, you can simply replicate that hierarchy / SOC serial at 5C0000, and then you override the status property. That's one way of doing it. The other way of doing it, which is exactly equivalent in the resulting DTB, is that at the DTSI level, not only you have a name for the node, but you also have a label, usart1, which is before the colon. And when you have that label, you can use it in the DTS to extend or override that node with extra properties just by using that label. You do %usart1, and then you override whichever property you want. So you don't have to replicate that hierarchy. You can simply say, for this specific node, I would like to inject more properties because I need to specify additional things. And this solution is now usually preferred in the Linux kernel. I think originally when we started doing device tree in Linux, the solution on the left was more common, but it became pretty clear over time that the solution on the right was a bit lighter and easier to maintain, and so it is the solution that is preferred today and that you will find in most DTS file and DTSI files. So now that we have looked at this concept of device tree inheritance, let's see how it applies to the STM32MP1 world. Of course, this is specific to the MP1 world, but in practice, if you look at other system-on-chip families, you will find more or less the same ideas. Of course, the implementation details will be different, but conceptually it will be very similar. So on this diagram, I have really split the things in two parts. The top, which is the files that describe the SOC, so everything that is above the dashed line, describe the SOC level information, and everything that is below the dashed line describe the board level information. So let's start with the purple boxes on the left, on the top left. We have the base device tree, STM32MP1 51. if you remember, the 151 is the lowest end of the processor in that family, the one with the smallest amount of feature. It has a single Cortex A7 and kind of the base set of peripherals, which is still already plenty, but the base set of peripherals. So this is kind of the base of that device tree organization. This is where we will describe the A7, the interrupt controller, all the I2C controller, UART, SPI controller, MMC, and all those base peripherals. And this file doesn't include any other device tree. It's really kind of the root of the description. Based on that, there is a STM32MP1 DTSI, which includes the 151, because indeed the 153 is a superset of the 151 functionality. It is the same as the 151, but it adds a second A7 and 2 CAN interfaces. So this file is much shorter, as it only includes the 151 plus describes an extra CPU and 2 CAN interfaces. The 157 is a superset of the 153, so it includes the description of the 153 and extends it with a description of the GPU and the DSI display interface, right? Then towards the middle, we have a yellow box called STM32MP15XC.DTSI. If you remember, every variant is available every variant, 51, 53, 57, are themselves available in 2 variants, with security, without security features. If you have the security features, the ones named C, then you have a crypto engine. And so this yellow box, which represented a DTSI file, only contains the description of a single hardware block, the crypto engine. Then in green and in blue, we have description of Pinmuxing configurations. And we'll get to Pinmuxing later on and how they interact with the rest. The reason why we have so many blue variants is because in addition to the different variants of the SoCs that we have discussed, the SoCs are also available in different packages that have more or less pins and that expose more or less functionality to the outside world, changing a bit the set of GPIOs and pins that you can actually use on your board. And these AA, AB, AC, AD names are actually named after the type of packages that you can get. And when I'm talking packages, I'm talking like BGA packages or things like that, really the type of package for the ICs. So that's for the SoC level representation. And then for the board level representation, how does it work? It is quite smart how they did it. They have at the center, we have this STM32MP15XX-DKX, that's a lot of X all over the place, which obviously serves as a wildcard, .DTSI. This file describes all the features of the board that are common to the Discovery Kit 1 and Discovery Kit 2. If you remember, the audio codec, the PMIC, the HDMI transceiver, and all these features were common to both the DK1 and DK2. So we would find these into these common DTSI files. And finally, we have the DTS files themselves, and we've got 2. One for the Discovery Kit 1, one for the Discovery Kit 2. And these DTS files, they start by including all the DTSI that they need. So let's start with the DK1. The DK1 is based on the 157 SoC, so it includes that DTSI. It includes the DTSI for the Pinmux configuration, as well as the GPIO definitions for the appropriate package. So the package is AC in the case of that board. And it also includes the common definitions between DK1 and DK2. And in addition to that, it can also add extra definitions specific to the DK1. The DK2, on the right side of the picture, does pretty much the same, but not quite exactly the same. Indeed, the variant of the SoC used on the DK2 has security features. So it's going to also include, in addition to the 157, it's going to include this 15xc.dtsi, which describes the crypto engine. It's going to include the pin configurations and GPIO definitions specific to the package and the common definition for both DK1 and DK2. But the DK2.dts is going to be also a bit bigger because the DK2 is kind of a superset of the DK1. It has, if you remember, the Bluetooth Wi-Fi chip, it has a display panel, it has a touchscreen, so it has quite a few features that will be described in the DTS itself. So as you can see, we really leverage this mechanism of inheriting device tree to avoid duplicating hardware definition in different files. We really split out things into different files in the smartest way possible, so that we have the least amount of information to replicate in our device tree files for specific boards. But it also means that you need to navigate around all those files and get your head around this organization to properly write a device tree file for your board. So some device tree principles. The device tree, one of the foundation principles of the device tree is that it is there to describe hardware, how the hardware is. Not how you use the hardware, like in what specific mode or configuration you would like to use your hardware, but very objectively, it should describe what your hardware is. I have an I2C controller, and it is connected to an audio codec at that address, and it has this and that, which I can objectively see in my schematics. Also, it should be operating system agnostic. So for a given piece of hardware, there should normally be only a single possible device tree representation for it, which should be the same for Linux, for FreeBSD, for U-Boot, for Barebox, for TFA or other projects. So there should be no need to change the device tree when updating the OS. Also, the device tree should describe the integration between hardware components and not the internals of the hardware components. So it should again describe, I have an I2C controller connected to an audio codec on this bus at that frequency, and there is maybe a reset GPIO that is used, so that's really how they are connected together. But it should definitely not describe the individual registers of your I2C controller or the individual register of your audio codec or some internal details of them. This should be hidden in the drivers. Really, the device tree is here for describing the topology and integration of hardware components together. Obviously, like all beautiful design principles, these principles are sometimes violated, so it's not perfect, but it's good to have this vision in mind to understand device tree files and how to extend them in the correct way. So what do we put in device tree files? How do we know all those nodes and properties to describe a given hardware platform or a given piece of hardware? Well, the base foundational document is the device tree specification document. It is available at devicetree.org, and it gives a specification for the base device tree syntax, like the CPU node, the memory node, the chosen node, the very basic properties. But this spec really only specifies this kind of base definition, which is not sufficient to really describe the wide variety of hardware that we have. So on top of that spec, we have the concept of device tree bindings. The bindings are documents that each specify how a given piece of hardware should be described in the device tree. So they tell which properties you should use to describe this particular audio codec, this particular I2C controller, this particular display panel, or Ethernet PHY, or any other piece of hardware that you might have on your system. These documents are stored in the Linux kernel sources in documentation device tree bindings. I think here again, very much like the DTS files themselves, the kernel kind of serves as the reference for those bindings. And indeed, these bindings, they are written by kernel developers when they write a driver for a piece of hardware that will be used in a device tree based platform. They will also have to write a corresponding device tree binding document, which will be reviewed by a team of maintainers in the kernel community, the DT bindings maintainer team, to make sure that the binding that you submit kind of makes sense and complies with the general device tree principles and design guidelines. In the past, those documents were written just as kind of basic human readable text documents. And since a few years, we have moved to using instead device tree bindings written in YAML so that they can be machine parsable. So let's have a look at a few of those documents. The first one I'm using is a legacy style binding because it's just written in human readable text and you can fairly easily see what it contains. For a specific IP block, a Spear SMI, it's not used on the STM32MP1 because on STM32MP1 all of the bindings that I could find were already converted to YAML. So ST did a good job there, and a good open source citizen. They already converted over to the new method for describing bindings. So I had to find an older example, which was not yet converted. And as you can see in the document, it simply says, to describe this piece of hardware, you need to write those required properties. What are the possible values and what they mean? What are the optional properties? And you've got a small example. In YAML, it's a little bit less readable for a human, but it has the big advantage of being machine parsable so that we can write tooling to validate bindings, and I'll get to that. But overall, it gives pretty much the same amount of information, right? It says what the binding is for. So this is for the I2C controller embedded in STM32 platforms. It is maintained by someone, and it has a bunch of properties: compatible, interrupt, resets, clocks, DMAs, clock frequency. Some of them are required, as you can see at the very end, at the bottom right of the slides. The required properties are compatible, reg, interrupts, resets, and clocks. So it really defines what we expect from the device tree representation for that particular device. And there is an example that shows how this representation gets used. So this YAML view is used for validation of the device tree. Indeed, as I mentioned earlier, DTC only does a syntactic validation. It is not capable by itself to find that this property doesn't make any sense in the context where you've added that property. But with YAML bindings, we can do that validation because we know that this I2C controller for the STM platform expects this and that property with that and that value. And if that property is missing, then there is a problem. So the Linux kernel has integrated this validation tooling. There are various make rules that you can run to benefit from that validation. The first one is make DT binding check, which verifies that the YAML binding themselves are valid, like they are correct YAML that you can parse. The one rule that is interesting is make DTBs check, because it is the rule that will check and validate the device tree files that you have against the YAML bindings. So it will tell you, ooh, this device tree file that you have written violates this aspect of the binding because it lacks a property, or it has an incorrect value for that property, or it has this property that doesn't make sense in that context, these kind of things. You can also reduce the scope of the validation to one specific binding, because those tools kind of take quite a bit of time, so sometimes it's nice to validate just on one specific binding using the DT schema files variable. So with that said, it's good to have a look at a number of really important standard device tree properties. And the one we're going to start with is probably the most important of all, the compatible property, which we have already encountered in the many examples before, but we need to define more precisely what it means and what it is used for. So first of all, from a syntax point of view, it is a list of strings, and they should be from the most specific to the less specific. And I'll get to that in the example. And this compatible property describes the specific binding to which the node complies. So it is this string that allows us to know, okay, this node is described by this binding document, all right? And this string is also used to uniquely identify what the device tree spec calls the programming model of the device. So to put it simply, the programming model is what is the set of registers and the meaning of those registers for that particular device. You have an audio codec. It has maybe registers at offset 0, 4, 8, 12, 16. The first register is for controlling the volume. The second one is for controlling the routing of the audio. The third one is for controlling the clock of something in your audio codec, and so on. So they have a meaning, they have a semantic. And this is what we call the programming model of the device, what a driver for this device needs to know to program and interact with that device. And so this is kind of an abstract view. More practically, the compatible string is used by the operating system to find the appropriate driver for this device. Indeed, if you have a driver for an audio codec that understands this programming model, that knows how to program this particular audio codec that has register 0 for controlling the volume, register 4 for controlling this and that, and so on, then this driver advertises that I can support this and that audio codec. Your device tree with its compatible string in a specific node will say this node represents that particular audio codec, and if there's a match between the two, there will be kind of a connection between a particular device and a particular driver. When describing real hardware, the typical form of a compatible string is vendor, model, like as shown below, ARM, ARM v7 timer, or ST, STM32MP1 DT Mac, etc. The two last examples are not really real hardware, like regulator fixed is to represent a fixed voltage rail on your system, like you have a fixed 5 volt or 3.3 volt voltage rail, and that you need to represent in a device tree. For other devices to use as a source of power, you can use that compatible string. Or GPIO keys is a Linux driver that uses a GPIO to create a kind of a keyboard that can be seen as from user space applications as a regular input device providing key events. So again, this is not really real hardware, it's kind of an abstraction on top of the GPIO hardware. Hence the fact that it doesn't have this vendor, model naming. Back to the second example here, you see that this compatible property has two values, and from the most specific to the less specific. So this allows to identify different drivers depending on their capabilities pretty much. So what the kernel will do, and what other operating systems have to do, is they have to look at the first entry, ST, STM32MP1 DT Mac, and check if there's a driver that recognizes that. If it is, great, we have the most specific driver for that device, that's good, we're gonna use that one. But if there's none, we can say in the device tree, okay, but if you have a driver that knows about SNPS DW Mac 4.20a, then it should do the job as well, because our hardware block is kind of the same. Maybe it has additional features on top of that, but with that specific compatible string, it can also work. And then the kernel will go and search for a driver with that and hopefully find a driver which may not be the best, but should be sufficient for that. That's why we order them from the most specific to the less specific. Another special value is simple bus, which is a compatible value that you can use to say this node is describing a bus of memory mapped devices. So all the sub nodes will each describe memory mapped devices. This is explained in a little bit more details in that slide. So the rule is that every top level node in the device tree that have a compatible property, and all subnodes of a node that carries the simple bus compatible value will cause Linux to identify each of those nodes and at boot time convert them into platform devices. So in the Linux kernel, platform devices are devices that are sitting on memory mapped buses. So if you look on the right side of the picture, we have a timer node at the top level. It has a compatible string. So when the Linux kernel boots, parses that device tree, it is going to instantiate a platform device structure representing that timer in the kernel memory. Then the DT parsing continues. It encounters the SoC node, which has this simple bus compatible property. So every subnode of that is going to be a platform device as well. So UART at 1000 is going to be a platform device as well, representing the UART controller. The I2C at 2000 is also going to be a platform device. It's one of the I2C controllers in our system. And then, as you can see, there is a subnode inside this I2C controller. And this subnode, because it is a subnode of an I2C controller, it is going to be instantiated by the Linux kernel as an I2C device. If that was a subnode of an SPI controller, it would be instantiated as an SPI device. So this kind of parsing of the device tree and conversion to in-memory data structures that make sense for the Linux kernel takes place at boot time. Then each Linux kernel driver has a table of compatible string that this particular driver supports. It's a table of OF device ID structures. And when there is a match between the compatible string of a node in the device tree and one of those entries in that table, then the device is bound to that driver, and that allows the driver to know, ooh, I have a new UART, ooh, I have a new audio codec, ooh, I have a new I2C controller, etc., etc. Let's have a look briefly at two examples of driver code in the kernel. First, the STM32USART.c driver, which is the driver for the UART controller found on those ST ICs. At the bottom, we have a platform driver structure. Indeed, this whole file is describing a driver for platform devices that sit on a memory map bus. And deep down into this structure, there is an OF match table field. That's kind of the last field on that slide. This table, which is at the beginning of the slide, STM32 match, is the list of compatible string that this driver supports. So if there's any node in the device tree that matches those compatible string, then the probe function of that driver will be called once for each of those devices. So if we have 4 UART controllers into our processor, there will be 4 nodes in the device tree, each describing one of these UART controllers. Most likely they will be of the same kind, right? They will have each the same programming model, the same register set, just duplicated 4 times to control the 4 different UART controllers. And because we have 4 of those nodes, there will be 4 platform devices created, and all of them will match with this list of compatible strings. And therefore, the probe function of that driver will be called 4 times, once per each UART controller available in the system, giving then in your Linux system 4 UART ports that you can use in your applications. Next driver is an I2C device driver, just to show how identical the matching principle is. In this driver, we don't register a platform driver structure, but an I2C driver structure, because it's not the same hardware bus that we rely on. But this structure also has an OF match table. And you can see it has pretty much the same syntax, just this one happens to only support a single compatible string, Cirrus, CS42L51. So whenever an I2C device is encountered with a compatible string of that value in the device tree, the probe function of that driver will be called. Really similar principle. So compatible, the most important property of all. The next property that we really need to discuss is reg. Reg has a different meaning depending on where it is located. For memory mapped devices, it contains the base physical address of the registers and the size of the register areas. Because they are memory mapped, we have a base address and we have a size of the register area. And we can have several entries if we have multiple register areas. And this is illustrated in the example below. We have 2 register areas, one at 5002700 for 4 bytes, and we have another area at 500273F0 for 16 bytes. For I2C devices, we also have a reg property, but it has a completely different meaning. It contains the address of the device on the I2C bus, which is also important to be able to communicate with the device, but it is definitely not an address in memory because I2C devices are not memory mapped. For SPI devices, the reg property contains the chip select number. Here we have an example of a quad SPI controller to which 2 memory flashes are connected. They are actually the same memory flash, just there are 2 of them. One is connected to chip select 0, hence the reg equals 0, and the other one is connected to chip select 1, hence the reg equals 1. The unit address of nodes must be the same as the first address, well, the address of the first reg entry. So the unit address is found in the node name. If you look at the example here, we have the label SAI4, which is before the colon, and then the node name is SAI at and this address. And this address after the at is called the unit address. And the device tree spec says that it must be the same as the address of the first reg. So it is kind of a unique identifier for this IP block. Indeed, if you have multiple, let's say, UART controllers in your system on chip, you will have multiple UART nodes in your device tree, but you would like them to have unique names. And a good way to have unique names is to simply use at and the base address of the register for this particular UART controller, because this is going to be different from one UART controller to the other. I don't need to introduce the concept of cells. We've already seen a bit some aspects related to cells, but without making it clear, so now it's time to do so. So in device tree, we represent integer values as 32-bit integers that we call cells. So on the right side of the picture, you have a property, foo, which contains a 32-bit value, dead beef, which is just one cell. If you want to represent 64-bit values, you need two cells of 32 bits each. And then we have properties that indicate how many cells we need to use in other properties. So this is kind of weird, and that's why taking a little bit of time to explain that is important. We have those properties that we have seen in few examples before: sharp address cells, sharp size cells. First of all, they are not comments. Even though they start with a sharp, and sharp is often used for comments in Python, in Perl, in Bash scripts, and so on. In that case, in the case of the device tree, they are not comments. Comments in device tree are using C++ style comment like // /*, things like that. So these are not comments. The sharp means number of, so number of address cells, number of size cells. And these properties, they indicate in the subnodes how many cells are used in the reg property to encode the address and to encode the size. So if we take the example on the right side, we have an SoC node, which is this very often this kind of top level node that encloses all the hardware blocks inside our system on chip. It says address cells 1, size cells 1. It means that every subnode, such as I2C at F1001000, if it has a reg property, this reg property must have one cell for the address and one cell for the size, which is correct here. We have one cell for the address, OX F1001000, and one cell for the size, OX1000. All right? And this mechanism, we have it in not only for address cells and size cells, but here you have an illustration with interrupt cells, which we use for interrupt controllers. I'll have a more detailed example about interrupts a bit later, but that is another example. In this example, we see that the interrupt controller, the node interrupt controller at something, says sharp interrupt cells equal 2. And the node at the bottom, the I2C controller, which uses interrupts, says I have interrupts from this interrupt controller, and to describe that interrupt, it needs to provide two cells, 12, 24. So what they mean depends on the binding of the interrupt controller, and this is a completely invented example. But to make the syntax correct, if the interrupt controller says I need two cells, then the interrupts property need to also have two cells. And this is the same for clock cells, GPIO cells, PHY cells, PWM cells, DMA cells, and many other similar properties that indicate to consumers of a particular resource how many cells they need to use to refer to a particular resource that is provided. Let's continue our exploration of properties. The status property is here to indicate if a device is really in use or not. So its value can be OK or OK, just two letters, to mean the device is really in use, or it can be any other value. By convention, we use disable, but I think really it can be anything else, in which case the device is not in use. So in the context of Linux, it really means and controls if a device is instantiated. If you have a node in the device tree with status disabled, well, the kernel is just going to skip over it and not even instantiate a platform device or an I2C device or an SPI device based on it, which means that the kernel will not take care of that device at all. So what is very often done is that in DTSI files that describe the system on chip, we usually have most of the devices that interface to the outside world that have status equal disabled. Indeed, at the time we write a DTSI, we don't know on the specific board where this processor will be used, which hardware interfaces will physically be used. Will you use the I2C controller 0 or 1? Will we use the display interface or the network interface? Will we use this audio interface or this other audio interface? This is not known in the DTSI itself. So we usually have in DTSI, everything is disabled, and it is up to the board-specific DTS, which knows, okay, this audio interface is used, this I2C controller is used, this UART controller is used, so I'm going to enable them, but everything else I leave disabled. So that's the idea of using that property setting it to disable in the DTSI, and overwrite that value in the DTS. I was mentioning that we would give more details about the interrupt description. Now it's time. So to describe interrupts, we have nodes to describe the interrupt controllers, and that's on the right side of the picture, the top node, interrupt controller at A0021000. It is a geek interrupt controller for ARM, which we find in a wide range of ARM SoCs. It says this is an interrupt controller by having the Boolean property interrupt controller semicolon. And it also gives a number of registers, because that's a hardware block like any others, memory map registers to control the interrupts. So we have two values in that reg property. And it also says sharp interrupt cells equal 3. So that tells us how many cells we need to use in consumers of interrupts managed by that interrupt controller. And so at the bottom of the example, we have two illustrations of using the interrupts from that interrupt controller. The first one relies on two properties, interrupt parent and interrupts. Interrupt parent indicates for all subnodes which interrupt controller is used by all the subnodes. So the fact that we have interrupt parent equal &inc at the top of the SoC node means that every other IP block that is described down will use that as an interrupt controller unless otherwise overridden at some other point in the device tree. Right, so when this SPI controller says geekspy 36 RQ type level high, it gives the type, number and flags for an interrupt. And this is 3 cells, right? geekspy, 1 cell, 36, second cell, RQ type level high, third cell. So we are right, we match with this sharp interrupt cells property. And this interrupt specification is related to the interrupt controller identified by the node that has the INC label because of this interrupt parent property. The example at the bottom indicates interrupts using a different property, interrupts extended, which is basically the combination of both in just a single property. Indeed, we specify the interrupt controller and then the specification of the interrupt. So INC geekspy 100 RQ type level high is one interrupt. INC geekspy 101 RQ type level high is a second interrupt. And look, we have a third interrupt that comes from a different interrupt controller. So the XI node is not on my example because I couldn't make it fit on the slide, but it's another interrupt controller available on this platform. All right, so that's the two ways of describing how a particular piece of hardware uses interrupts from an interrupt controller. And this way of representing the integration and connection of hardware blocks between each other is really a pattern that we see for all the other resources that you can have in a system on chip, for clock controllers, DMA controllers, reset controllers, and so on. And I've chosen to illustrate that briefly with the example on the right side. At the very bottom, you have an SPI controller. It has a bunch of properties, but the one I would like to focus on are the clocks, resets, and DMA's properties. The clocks properties says which clock is provided as an input clock to this hardware block. And as you can see, it is &RCC, and RCC is a node at the top of my example, which describes a clock controller. RCC stands for reset and clock controller, which is on this specific piece of hardware, an IP block that controls the different clocks and the different reset signals inside the system on chip. So this SPI controller is using the clock labeled SPI3_K. It is using a reset signal from that same controller named SPI3_R. And you can see this second part of the property, SPI3K, SPI3R. There's one extra cell in addition to the P handle, the pointer to this other node. And that matches really well with sharp clock cells equal 1, sharp reset cells equal 1. This clock and reset controller wants one cell to describe which clocks get used or which reset line gets used. If we continue, the DMA's property indicate which DMA channels are used by this SPI controller. And we have a P handle to the DMA MUX node, which describes a DMA controller. And this DMA controller tells us you need 3 cells to describe a reference to a particular DMA channel. And indeed, in the SPI controller node, we have $DMA MUX1, pointer to the DMA controller, 61 OX40 OX05. I have no idea exactly what they mean because I haven't looked up the binding for that specific DMA controller, but these information are needed by the DMA controller to identify which DMA channel to use and maybe how to use it, how to configure it. And again, hopefully you see kind of the pattern here, which you will find in many device tree files for various resources provided by hardware blocks and used by others. These reference to resources in various properties are sometimes associated to a corresponding prop names property. So for example, interrupts, you might have an interrupt names property. Clocks, you might have a clock names property, which are really tied with each other. And basically these names property, they give nice human readable names to the entries. So for example, here you have interrupts equal 0590, 070, and we can give names to those 2 entries, MAC RQ and MAC PMT. So not only that makes the device tree a little bit more readable, but it also allows the driver code to do something like platform get RQ by name and say, I would like the MAC RQ. And it also allows us to give the interrupts in any order we want, right? We could swap around the 2 interrupts and swap around the 2 names, because the first name corresponds to the first value of the interrupts property. The second names correspond to the second entry in the interrupts property. So that also provides a bit of flexibility on the ordering of the fields. And you can find that for, again, interrupts, clocks, resets, DMA channels, and many other things. Let's talk a bit about pinmuxing, because this is something that very often people struggle with, and is also something which is very often the first contact with the device tree, because you very often have to configure pinmuxing when you want to simply plug something into an existing board. So in most modern processors, including the MP1, there's typically more feature inside the processor than the package has pins to expose all those features to the outside world. So what those processors do, they mux pins, which means that a particular pin going outside of the package can only be used at a time for one function or another, but not both. And this is illustrated with the diagram on the right side. We've got just 2 pins going outside of our SoC package, but internally those pins can either expose a GPIO, or for the first pin at the top, or a UART receive line, or a SPI controller master in slave out line, or a clock line for an I2C controller. So you have to choose by configuration, by software configuration, which of those 4 features is currently exposed on that particular pin. And all of that is controlled using the device tree, which describes which pinmuxing configurations are possible and which one you actually want to use on your particular system. On STM32MP1, there are 2 Pinmux controllers. So there are actually 2 sets of registers that are used to control that. And so you have 2 nodes in the device tree, pin control and pin control Z. And it turns out that those registers also control the GPIOs. So to control GPIOs, like put a line high, low, and things like that, it's also done within the same areas of registers. So as subnodes, we have the GPIO banks, GPIO A, B, C, D, E, F, and so on for the first one. And the second one is smaller with just 1 bank of GPIOs. So this is in the DTSI file for the SoC. And then you have definition inside that node, right? You can see ampersand pin control. So we are, all what we're seeing here is in fact inside the pin control node that we've looked at on the previous slide. And this shows different pin configuration. Here we have 2 pin configuration, I2C1 pins A and MCAN1 pins A. So it's a configuration for an I2C bus and a configuration for a CAN interface. At the moment, it doesn't say that they are used. It only says these configurations are possible. Let's look at the first one for I2C. And it says that it configures 2 pins, pin D12 in function AF5 and pin F in function pin F15, sorry, in function AF5 as well. And there are some very nice comments that tell us what this means, but you can also check it up in the datasheet. If we look at pin D12, we open up the datasheet. It looks like this. It's a pin of port D, and in this table we can go in the line PD12, which is somewhere to the bottom. And this pin PD12, as you can see, can be one of different functions. Like if you configure AF1, it's going to be some kind of timer input. AF2 is going to be some kind of timer channel 1, and then AF3 another timer input. Function 4, it's going to be the clock for the I2C controller 4, and function 5, which is the one we're interested in, it's indeed configuring that pin to have the function of being the clock of the I2C controller number 1, which is what we're using here. So this is describing a possible way of getting the signals of the I2C controller number 1 out of the SoC on two pins, D12 and F15. Now, in our board, when we create the schematics of the board, we decide which pins are going to be used for what. And so we will have to tell in our board DTS which specific pin configuration we will use. So when we describe the I2C bus on our board DTS, we will have to use these pin control properties that are visible on the slides. Pin control 0, pin control 1, pin control 2, pin control 3, etc., and pin control names. So the reason why we have multiple of those properties is because you can describe multiple states of pin configuration. Here we have two states. We have the state described by pin control 0 and the state described by pin control 1. And they are mutually exclusive. You can either be in one state or in another. In this particular example, the two states are default. So you can see in pin control names, the first string, default, identifies the name of the first state, described by the pin control 0 property. And we have a sleep state, second state in pin control names. It corresponds to the pin control -1 property. And so the driver can, on its own, decide to switch between one or the other states. And in practice, in this case, what this is doing is that default is the state, normal state for the pins to be functional. Like when you want to really use that I2C bus, they need to be in that state. But also if you want to save power, like for example, if you put the entire platform in a low power mode, you can save power by changing the configuration of those pins to a kind of a sleeping state. And the driver can take care of that. It has some power management callbacks that get invoked when going into a low power state or returning back to a fully operational state. So the driver would do this transition from default to sleep and from sleep to default. In most cases, you usually only have a single state called default with a single property pin control -0, and a state called default is automatically set up and configured when you boot the system and when the driver is initialized for that particular device. To now put that in practice on hardware, let's have a look at the changes that we need to do on a device tree to describe an LED and an I2C device connected to the DK1 Discovery Kit platform. To do that, we'll start by creating our own device tree file. We'll call it STM32MP1 DK1-custom.dts to contain our customization. And we do that in the Linux kernel, so it's in Arch ARM boot DTS. And for now, in this DTS, we're simply going to be including the DTS describing the Discovery Kit. So just one line in our device tree, simple. We go into Arch ARM boot DTS makefile, and in this file we can instruct the kernel build system to also build our DTS into a DTB. So this makefile associates some kernel configuration option, config arch STM32, to the list of device trees that needs to be produced. So we simply add our own next to the one for the DK1 board. Then we can run the kernel build, make, or more precisely make DTBs if we want to build just the DTBs. And we will see the kernel build system invoke DTC to compile our new DTS into a DTB. We can use it and boot our board, and we would obviously see absolutely no difference at this point because we're simply including an existing device tree without making any changes to it. It's time to make some changes. First change, we want to describe an LED. And this LED, we have connected it to one of the Arduino connectors at the back of the discovery kit, and we've kind of arbitrarily chosen pin 3 of that connector, which happens to be the pin PE1 of the SoC. So in the device tree, we have created a LEDs node, and in this node, we are using the GPIO LEDs compatible string, which uses a Linux kernel driver that turns any GPIO into an LED from the point of view of the Linux system. Every subnode is going to be a separate LED. In our example, we have only one that we called webinar. We give it a nice label, which is in fact the same, and we tell which GPIO this is using. And this is the GPIO number 1 of bank GPIO E. Remember, it's PE1, the pin, so it's GPIO 1 of the bank GPIO E, and we say it's active high. I recompile my device tree, I reboot my platform with that device tree, and bing, in sys-class LEDs, I have a new folder called webinar, which corresponds to my LED, and when I echo 255 in that brightness file, it turns up my LED. If I echo 0, it turns off the LED. Slightly more complicated example, connecting an I2C sensor. Here we have a BME 280 sensor, a Bosch BME 280, which is a temperature, humidity, pressure sensor. And we've decided to connect it to pins 9 and 10 of connector CN13, because those pins very conveniently provide access to the I2C bus 5. You can see I2C 5 SDA, I2C 5 SCL. So nice, we have a clock and data, so let's plug it there. So in the device tree on the left side, we are extending the I2C 5 node, which exists, right? The I2C 5 node is described in the STM32 DTSI files. It's an I2C controller from the SoC, but we are going to extend it. First, we enable it. Say status, okay, we want this controller to really be instantiated in the kernel. We specify the clock frequency at which the I2C bus will be operating, 100 kHz. Then we specify the Pinmux configuration with those two states, default and sleep. And here we can use an existing Pinmux configuration, of course, after checking that this configuration is indeed going to be configuring PA12 as the data line and PA11 as the clock line, as can be seen on the right side and in the board datasheet. And finally, as a subnode of the I2C controller, we describe the particular I2C device that we have connected, which is this Bosch BME 280. It already adds a driver in the kernel, it already has a device tree binding, and its device tree representation can be as simple as just providing the compatible string and the address of the device on the I2C bus, which is here OX76. With that done, we compile our device tree, we make sure that the BME 280 driver is enabled in our kernel configuration, we boot, and bang, in sys bus IIO, we have a new folder corresponding to our BME 280 device. So why IIO? Because IIO is the Linux subsystem for that stands for industrial input and output, which is basically used for a lot of different types of sensor, temperature, humidity, pressure, and accelerometers, ADCs, lots of different types of sensors. And we can get the temperature of that sensor, humidity level, and other things in different files. If you want more details about that specifically, we've written a fairly detailed blog post that describes all the steps to bring up a sensor like that connected to the STM32 platform. And in fact, this particular blog post itself is part of a larger series of blog posts that we have written and published, which describe from the very beginning how to build and embed the Linux system for the MP1, from creating a basic build root configuration, connecting an I2C sensor, setting up an environment for developing a Qt graphical application, actually developing that application, showing measurements of the sensor on the screen, integrating remote updates, doing factory flashing, and so on. So if you're interested, I recommend you to check it out. It's available on our blog. So this is kind of concluding our device tree discussion for today. But there's more. I was hoping to be able to cover the entire device tree in an hour and a half, but there's still more topics than that. We haven't covered the range property to describe address translations between buses. We have not covered complex device tree bindings such as the ones used for audio, display, camera devices, or PCIe. We have not discussed the Linux kernel APIs provided to query information from the device tree. You can, from a kernel driver, look at the device tree and find which property is there and parse those properties and so on. We haven't discussed the tooling available in U-Boot to manipulate the device tree. We have not discussed the concept of device tree overlays. So there's many more we could discuss around device tree, but hopefully this was already a good and solid introduction for you. Here are some resources. The device tree spec, very important. On top of that, the device tree bindings, which we mentioned. If you're interested, you can check out my previous device tree for dummies talk, even though I believe, and hopefully this webinar is kind of a more extended version of that. The eLinux wiki has a very good page on device tree with plenty of reference to other documents. And they also have on the eLinux wiki a page that is a compilation of references to all the talks that were given at embedded Linux conferences over the past 10 to 15 years on the topic of device tree. And you will find lots of details on device tree validation and usage of device tree, concerns around device tree, and so on. So to conclude about the device tree, the DT is a representation of non-describable hardware in the form of a tree of nodes with properties. There is some standardization that is based on device tree bindings. It's a new description language which has lots of properties and sometimes complex bindings and complex topics, but it is no use for numerous CPU architectures. It's widely used in the Linux kernel, but also outside in U-Boot, Barebox, and other projects. And so it has become really a must-know for all embedded Linux developers. And I hope this discussion will help you understand that better or discover that and help you for your future projects. A quick reminder about Bootlin. Again, we are a company with expertise in embedded Linux. We have training and engineering services. We can develop PSPs and drivers. We are strong open source contributors, so do not hesitate to contact us. And again, I would like to thank a lot ST for supporting this webinar. And now we can get started for the Q&A session. So I'm going to switch to a different scene and bring up the chat and hopefully start answering your questions. So give me just one moment and switch to the chat. All right, so let's see if there are a few questions. So my colleague Alexandre Belloni was already there in the chat throughout the discussion, and I see he has been busy replying to a number of questions. So let's pick up one of the questions that Alex has already answered, but what does the 76 mean at the pressure node? So indeed, this node is this value is the address of the device on the I2C bus. Do we have other questions? Let's see, kind of scrolling down, I'm seeing some thank yous. Let's see if we've got other questions. All right, I don't see many other questions. How is a microcontroller different from a microprocessor? Indeed, one could wonder what is the difference. Very often, I think the difference is mainly around two aspects, whether it has a memory management unit or not, even though it's not the one thing that makes a very clear-cut difference between the two. But very often when you don't have a memory management unit, it's more a microcontroller class of devices, and when you have a memory management unit, it's usually more considered to be a microprocessor class of devices. I think the difference is also the type of operating system that you run on that sort of platform. On a microprocessor, you will find what sometimes most people call a rich OS, like Linux or some other OSs that have a concept of kernel space, user space, multitasking with privilege separation and isolation, and that kind of rich functionality, as opposed to more, I'm not sure they are more simple, but slightly simpler operating systems for microcontrollers, such as FreeRTOS, maybe Zephyr, NotX, and so on, which don't require a memory management unit and also have less separation between kernel user space and less abstraction layers compared to something like Linux. But obviously the boundary is not that clear-cut. For example, there are a number of non-MMU platforms that can run Linux, so you can configure them as microcontrollers that are strong enough to run a Linux kernel. So yeah, the boundary is not that clear-cut, I agree. So let's see if we have more questions. I'm seeing a lot of thank yous, so that's nice. I saw interrupt controller uses other nodes like a GPIO chip. Okay, that's a very good question. Indeed, a GPIO chip can be an interrupt controller itself, right? You have a GPIO chip to which a number of GPIOs are connected, and we might want to use some of those input GPIOs as interrupt signals. Like you have your touchscreen, it has an interrupt signal that you wire to a GPIO of your SoC, and so when someone pushes the screen, the touchscreen controller raises that GPIO line, and you would like your GPIO chip to render that as an interrupt. So a GPIO controller can indeed be not only a GPIO controller, but also an interrupt controller. That's perfectly correct. So, small question from the relation between kernel and U-boot. Why do you pass the DT when building Linux if the final DTB is passed by U-boot anyway? Actually, this was also a question raised earlier today in the first session of this webinar, so I guess some extra clarification would be needed in the slides. There are really two different things, right? There is the device tree that U-boot uses for itself, for knowing what is the topology of the hardware, and there is the device tree that the Linux kernel needs to understand the topology of the hardware. And they don't have to be the same, right? Of course, they will somehow need to be somewhat similar, right? Because it's the same hardware platform, but they don't have to be exactly identical. And U-boot might need a more reduced version of it than what the kernel has, but they can also be the same, right? And it's in fact also possible to ask U-boot, hey, you have a device tree block built into your code, please pass that to the kernel because it uses just the same. I think to understand a bit the current situation, you need to take a step back and look at the history of things. The Linux kernel started using the device tree on ARM32 first, and at that time, U-boot was not using the device tree at all for itself. So they first modified U-boot to be able to pass a device tree to the kernel. And then it's only later that people figured, oh, but it would be good to also use that device tree thing in U-boot itself, and so make that possible. So that's why we have this separation between the device tree used by U-boot, the device tree used by the kernel, and now we have this ability of, in fact, asking U-boot to pass the same device tree. But I'm not sure if this is so widely used. I'm not really sure, but I've never used that myself, and I don't really, yeah, I see the benefits, but also I believe there could be maintenance issue with that. If you want to change your device tree, it means that you need to update your U-boot. Yeah, I'm not sure that that's really a very good idea. And by the way, hello, Victor. All right, other questions? Can I access this video at some other time? The slides will be available. I think we will publish the video as well. Hopefully the video is not too bad, but yeah, we will definitely publish the slides and hopefully the videos as well. So another question was, when using appended DTB, how does U-boot provide the information it provides normally in the DTB? That's another good question. So the appended DTB is a backward compatibility mechanism that the kernel for ARM32 provides. It's not available for the ARM64 architecture, but on the ARM32 architecture it's there. It is there to support legacy bootloaders that did not support for device tree. And the idea of the appended DTB is that you take your kernel image and you append the device tree to it, and the kernel will recognize that at the end of its image there is a device tree. So from the point of view of the bootloader, you just load a big kernel image, which in fact is the kernel image plus the DTB, but from the point of view of the bootloader, it's just the kernel image. And so the bootloader doesn't have to know about the device tree, but your kernel will still be able to use that normal device tree representation. And indeed, the question being asked here is, in that case, how do you get the bootloader modifies the device tree to pass information to the kernel. Obviously it doesn't, because it doesn't know about the device tree. So in that case, what the Linux kernel does on ARM32 is that it can use the legacy mechanisms that were used before device tree to pass information from the bootloader to the kernel. And this mechanism is called A tags in the kernel. It's part of the boot protocol between a bootloader and the Linux kernel. And it's kind of another small data structure that the bootloader leaves in memory, passes that memory location into a register to the kernel. And this contains the kernel command line and the size and base address of the memory and a few other things, but it's very limited. It's by far nothing like the device tree. All right, let's see if we've got more questions. Is there any solution to choose device tree at runtime in U-boot, like having multiple device trees built into U-boot, like FitImage and the kernel, and choose which one to use at runtime? So as you mentioned, for choosing the device tree that U-boot will load and provide to the kernel, you've got plenty of options there, like you mentioned FitImage. You can also, from the U-boot command line, do some scripting and whatever. For the device tree built into U-boot itself, I'm not so sure what are the possibilities there. I'm not 100% sure, so I'd rather not say something wrong than say something. About pin configuration, is it always something that we have to fish up from the datasheet, assuming that they exist? I also wonder where constants like SPI3K come from. All right, so that's actually two questions. Is it always something that we have to fish up from the datasheet? It is indeed fairly common that to get the Pinmuxing configuration correct, you have to get the datasheet of your system on chip. There is often quite a few comments in the DTSI files that describe those Pinmux configurations, so sometimes you can get away with just the comments, but having the datasheets around as a way of double checking things is very nice. We have this joke at Bootlin that if your device you're working with doesn't work, first check your clock, second check your Pinmux, and if it's not any of these, check again. So Pinmux mistakes are very often the source for why you cannot talk to your device. So having this ability to double check with the datasheet is great. And your second question was, you wonder where constants like SPI3K come from. This is a very good question. I think I should have covered it, but again, time was limited. There is a set of header file in include/DT bindings in the Linux kernel that define a bunch of macros like SPI3K, like geekspy or RQ type level high. All those macro names are simply C defines, which get expanded by the C preprocessor. So that's where they are located. So many of them are kind of generic ones, and some are more specialized to a specific piece of hardware, like this SPI3K, SPI3R. So check include/DT-bindings in your Linux kernel source tree. Is it possible to modify the device tree and then compile it using buildroot? Yes, so of course. I mean, buildroot doesn't really build directly your device tree, but it leaves that to the Linux kernel build system or to the U-boot build system, for example. But you can definitely provide a patch against your Linux kernel tree, or you can even tell buildroot that you have a separate device tree file, and buildroot will take care of copying that into the kernel sources and build it as part of the kernel build process. So that is definitely possible. And I see that Giulio Benetti is giving lots of details about that. So thanks a lot. What tools, toolset or reads would you recommend for an embedded Linux beginner with his own eval board which utilize F1C100, which I'm not really sure what these are? So to really get started, there's plenty of books. Of course, I'm going to advertise our training materials. I have to do that. They are freely available, and I think they're quite comprehensive. So this is probably a good way of getting started. But there are also plenty of embedded Linux books that have been written over the years. Obviously, The issue is that they will probably not cover your exact hardware platform and they may be slightly out of date. But this is not such a huge deal. First, because most of the concepts on tools and principles are very hardware agnostic. So you will find detailed information and useful information even if it doesn't cover specifically your hardware platform. And second, even if the information may be like a few years old, in fact the concepts don't change too much. Like what I have been describing about the device tree, we started using the device tree in ARM32 around 2010, so it's been like 10-11 years now that we've started using like for real the device tree in ARM32, and things haven't changed that much. They have evolved a bit. We have the YAML bindings, we have some better tooling here and there, but fundamentally the concepts are still the same. Alright, so I think we've reached 7 p.m. here local time, so we've over 2 hours for this webinar, which I think is good. Thank you very much for your participation. I would like to encourage you to contact us at Bootlin if you have any further questions about the device tree or embedded Linux topics. We'll put online the slides of that webinar and the video as well, but don't hesitate to reach out to us for any question. Again, thanks a lot for your participation and have a good day, good evening, good night wherever you are, and take care. Thank you very much.